Hi, my name is Alana Duarte.
I'm Brett Cernich.
I'm Gabby Hansen.
I'm Colin Quinnell.
The practice of breeding and raising domestic animals for the purpose of fruit production, known as animal husbandry, has become an environmental concern due to its high consumption of scarce resources like land, water, and energy. Currently, animal meat serves as the primary source for dietary protein, but is an environmentally unsustainable solution, as an increasing population causes increasing demand of already scarce resources. Entomophagy, which is the practice of eating insects, has become a growing study of interest because of its limitedly explored potential to be a viable solution to this food crisis. Since the insect food products on the current market mostly include ground-up insects as flour for baked goods or as a source of protein powder, we wanted to explore a new way to capture the protein from insects for food. We chose to study chemical extraction from the protein from mealworms to incorporate into food, a process that has been limitedly explored so far by entomologists. The purpose of this project was to determine the best procedure to chemically extract protein from mealworms and translate it into an upscaled process. The first step to doing this was determining the best way to extract the protein. Let's get started!
We found a tested procedure to extract mealworm protein through chemical reactions in research literature, which became the basis of our experiments. To determine the optimal experimental environment for mealworm protein extraction, we tested the effects of 6 different conditions by varying one condition at a time.
An initial defatting step, NaOH concentration, ratio of NaOH to mealworm powder, number of reaction iterations, experiment temperature, and incubation time. Protein yields were compared to a control set of conditions found in the original literature. Experiments, we weighed 1 gram of ground mealworm, then poured into a 15 milliliter centrifuge tube. Sodium hydroxide was measured and added to the tube, which was vortexed every 15 minutes, and stored in an incubator to maintain a constant temperature. At the end of the reaction time, the tubes were placed in the centrifuge to separate the liquid layer from the mealworm solids. The centrifuge was set for 3,500 Gs for 20 minutes at room temperature. The liquid and supernatant layers were transferred to a new centrifuge tube. Hydrochloric acid was added until the solution was at a pH of 4.3. After another pass in the centrifuge, the solid precipitate was isolated and rinsed. PBS buffer was added to this solid to create a solution. 1 milliliter of Bradford reagent was combined with 20 microliters of this solution to quantify the protein amount. The sample is placed into the spectrophotometer to measure the absorbance at a wavelength of 595 nanometers. To ensure the sample concentration was within the calibration curve range, we diluted the sample using 15 microliters of PBS to 5 microliters of sample. The calibration curve was derived from a dilution set of known concentrations of bovine serum albumin standards.
The yields were calculated by dividing the amount of protein extracted by the theoretical amount of protein, which was calculated using the researched value that dried mealworms are 43% protein. The values for each condition that produced the highest protein yield were combined as the optimal conditions. The optimal conditions were determined to be 20 milliliters of 0.5 molar sodium hydroxide to 1 gram of defatted mealworms at 40 degrees Celsius for 2 hours, executed 3 times, with a maximal yield of 23%. The absorbance of pure Bradford reagent was subtracted from recorded values to get the adjusted absorbances. This relationship between adjusted absorbance and protein concentration were plotted as such.
Through literature research and our own testing, we discovered mealworms have a nutty seed-like flavor. They actually taste just like sunflower seeds. So to create the best recipes, we wanted to use ingredients that would complement that flavor profile.
We have a banana blueberry bar, which consists of eggs, bananas, maple syrup, milk, vanilla, oatmeal, blueberries, and of course, mealworm powder. Bake at 350 for 20 minutes. We have blackberry and peanut butter, which consists of peanut butter, honey, rolled oats, blackberries, and mealworm powder. Refrigerate for 1 hour to set. Last but certainly not least, we have salted dark chocolate and peanut butter, which consists of peanut butter, honey, coconut oil, vanilla, dark chocolate, Himalayan sea salt, and mealworm powder. Refrigerate for 1 hour to set.
Wow, these all look so delicious. It'll be real hard to figure out which one we like best.
And here are our products. We used a positive scoring decision matrix to pick the best recipe based on taste, texture, color, and consistency. After collectively scoring each bar individually, The peanut butter chocolate protein bar scored the highest, and we used this for our upscale process.
Using our optimal experimental conditions, we upscaled an industrial process to produce our protein bar. In order to receive about 1% of the revenue in the current protein bar market, we aimed to produce 2 million bars annually. We calculated the annual input to our process based on the experimental results of protein yield and mass lost through defatting. Then, based on our yearly input, in addition to the processing time per batch, we calculated the required daily input of mealworms. For adequate batch sizing, we decided to break up this daily input into 3 batches per day at 1,800 bars per batch. We split our overall process into 4 distinct sub-processes. The first of these is the Comminution Loop. This loop receives live mealworms as an input, euthanizes them, decontaminates them, and dries them to a safe-to-eat moisture content. Finally, the mealworms are ground into a flour using a miller and placed in a storage tank. From there, 57% of the mealworm flour is implemented directly into the protein bars, while the remaining 43% enters the defatting loop. The ethanol mixing and separation steps are performed twice to maximize the defatting. Additionally, we added a flash drum and condenser to our process to capture the extracted lipids and recycle the ethanol back to the process. The defatted mealworm powder is then sent to the protein extraction loop, where we implemented our optimal experimental conditions. Even though our results indicated that 3 iterations of the NaOH extraction steps maximized protein yield, the increase in yield was only slight, so we decided to stay at 2 iterations to reduce process time and increase profit margins. After the NaOH and HCl steps, the extracted protein is rinsed with water twice and then sent to the final loop of our process.
The protein bar product is made in the dough loop. First, the mealworm flour, extracted protein, and other ingredients enter a mixer. Then the dough is rolled out, given a chocolate coating, and sliced into bars. Finally, the bars are packaged to produce our final product.
Overall, our process outputs 2 million protein bars annually. Each bar contains 18 grams of protein, 10 of which are contributed from mealworms. This process offers an environmentally sustainable protein source for the current market and provides a viable solution to the growing global food crisis.
Woo-wee, this sounds like a heck of a project. Here are the 3 big areas for future improvement. Continue protein extraction experiments. By the end, we are extracting 23% of the available protein, which is quite an achievement in such a short time, but there is still quite a bit of room for improvement. More research into adapting the process to include other insects like crickets, and research into the in-house repurposing of the mealworm waste products into things like fertilizer.
We want to thank our instructor, Dr. Kim Ogden, our mentor, Dr. Savagatrip in his lab, and Dr. Roberto Guzman's lab.